Today we will work on a basic introduction to probability. I'll try to get fairly detailed as much as possible. We'll begin with the definition of an experiment. It is a repeatable task with well defined outcomes. A sample space is going to be all possible outcomes of a given experiment. An event corresponding to an experiment or a sample space is going to be a subset of the sample space of an experiment. Let's work out some examples. We will talk about experiments and their corresponding sample spaces. Suppose we toss a coin once, the possible outcomes being h and t, then the sample space is h comma t. If we toss the same coin two times, we will have a sample space of size 4 given as follows. And if we toss the same coin three times, we will have a sample space of size 8, which has the following 8 outcomes. Uh, Now, if we toss the coin three times and think of this as our experiment, we can think of multiple events. If we consider the event consisting of HHH, then this corresponds to the situation where the coin lands heads all three times. The event E2 corresponds to the case when the coin lands heads exactly once, or equivalently, that the coin lands tails exactly twice. The event E3 is slightly different from E1 and E2. In this case, one way to describe this event is that the coin lands heads on the first of the three tosses. Before we talk more about probability, it'll be good to set up some basic set theory. So if A and B are two sets, we can talk about A being a subset of B. This is to say that an element lying inside A implies that it lies inside B. This is sometimes called as the containment relationship between A and B. The equality relationship between A and B is going to be equivalent to saying that A is a subset of B and B is a subset of A. The empty set is the set that contains no elements. This is typically denoted by phi. Important property is that phi is contained inside every set. Some operations with sets are as follows. Suppose we have two sets A and B. We can describe the union of two sets, which is the set of all elements which are contained in either A or B. This is sometimes notated as A union B. The intersection of A and B is the set of all elements that are contained inside both A and B. This is sometimes said as A intersect B. And finally, the complement of the set A is the set of all elements that are not inside A. This is called the complement of A. Suppose we have an indexing set. Typically, we will consider the set of natural numbers as an indexing set, but you could have anything for an indexing set. And suppose we have A alpha for alpha inside gamma, a collection of sets indexed by gamma. Then we can talk about arbitrary unions and intersections. The arbitrary union is going to be the set of all elements x, such that x belong to some A alpha for some alpha inside gamma. And the arbitrary intersection is the set of all elements x such that x belongs to A alpha for every alpha inside gamma. We note the following. We will say that A and B are disjoint sets if the intersection of A and B is the empty set. Sometimes this is also stated as A and B being mutually exclusive. A collection of sets A1, A2, A3, and so forth is said to be pairwise disjoint if the intersection of AI and AJ equals the empty set for all choices of I and J that are not equal. We will say that a collection of sets A1, A2, A3, dot, dot, dot is a partition for the set S if A1, A2, dot, dot, dot is a collection of pairwise disjoint sets, and if the union of the AIs equals the entire set S. We will now work towards describing the probability function. To do so, we will have to start with a sample space of an experiment, which we denote by the symbol script S. And given an event that is a subset of S, we are interested in associating a number to E that might be a measure of how probable the event E is of happening. Before we decide to assign this number, we will first need to identify the events that we are interested in inside the sample space. A sigma algebra is exactly what would help us achieve this. A sigma algebra script B is a collection of subsets of the sample space S, which satisfies the following three conditions. We require that the empty set lie inside the sigma algebra. We require that if a set A lies inside the sigma algebra, then the complement of A also lies inside the sigma algebra. And finally, if we have a countable collection of sets A1, A2, A3, dot, 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 that lie inside the sigma algebra, the union of all the AIs should also lie inside the sigma algebra. Note that given a sample space S, there can be multiple sigma algebras that could be associated with the sample space. For example, if we were to work with the collection of sets, the empty set and the entire sample space, this would satisfy all the conditions for a sigma algebra, and it is typically called the trivial sigma algebra associated to S. If the sample space is finite or countable, then we can consider the collection of all subsets of S, including S itself. If we denote this collection by script B, then script B ends up satisfying all the conditions to be a sigma algebra. Typically, when we define sigma algebras, we will choose it in such a way that it contains all events that we are interested in. Let's do a concrete example. Suppose our sample space S is the set containing the following 8 elements. These are the outcomes of the experiment, which involves tossing a two-sided coin 3 times. In this setting, note that the sample space contains 2 to the 3 elements, that is 8 elements. And if we define B1 as the power set of S, that is, B1 is the set of all subsets of S, including S, then B1 is a sigma algebra that is associated to the sample space S. Note that in this setting, the cardinality of B1 is 2 to the 8. Notice that as the size of the sample space increases, the cardinality of this sigma algebra increases very quickly. On the other hand, we could consider another sigma algebra, B2, that is the sigma algebra that has generated by these 4 subsets of your sample space S. The way we construct sigma algebras by this process is by starting with a collection of sets and then tacking on countable unions and the complements and also the empty set. So if we define B2 as the sigma algebra generated by these 4 sets, then the cardinality of B2 ends up being much smaller than 2 to the 8. This sigma algebra is going to show up in a later video, but for now, let's understand that B2 helps us cutting down the events of interest inside the original sample space to a much smaller set. The price that we pay is that in the sigma algebra B2, we won't be able to distinguish between the events HHT and the event HTH. We refocus to our goal, which is to start with a sample space S and an associated sigma algebra script B, and we want to assign probabilities to events inside my sigma algebra B. This is achieved by defining what is known as the probability function for the pair script S, comma script B, where script S is the sample space and script B is an associated sigma algebra to script S. A probability function P is a function going from script B, the sigma algebra, to R, and it satisfies the following three conditions: that the probability of every event is going to be greater than or equal to 0, the probability of the entire sample space is going to be 1, and if we have a countable collection of sets inside the sigma algebra that are pairwise disjoint, the probability of the union is going to be the sum of the probabilities of AI. Note that these three conditions are sometimes called the axioms of probability and also referred to as the Kolmogorov axioms. Also, there can be multiple probability functions corresponding to a fixed pair uh, uh, of sample space S and an associated sigma algebra script B. Let's work out an example. So suppose we toss a coin once. In this setting, we will have the sample space S to contain elements H, comma T, and we can set our sigma algebra B to be the power set which contains the following four elements. One choice of a probability function is to define P sub half, which is going to be a function going from the sigma algebra B to R, and we assign the following values to the entire sample space S. We will get 1, and to the events H and T, we apply equal probability of half, and we require that the probability of the empty set to be 0. Then it is easy to see that P sub half is a probability function. In fact, for any choice Q, a number Q inside 0, 1, we can define P sub Q to be a probability function, that is a function going from B to R, which satisfies the following four conditions: that the sample space goes to 1, it takes the event H to Q, the event T to 1 minus Q, and the event empty set to 0. And we can see that P sub Q is also going to be a probability function for the pair S, comma B. This gives us an infinite family of probability functions for the pair S, comma B. Now, another way to generate probability functions for a countable sample space is as follows. If S is a sample space that is countable and script B is a sigma algebra of all subsets of S, we can consider a sequence of positive real numbers, that is, all the pi's are greater than or equal to 0 for all choices of I, and the sum I going from 1 through infinity of pi equals 1. In this setting, we can define the function p going from b to r as p of a to equal the sum of all the pi's such that the corresponding si's lie inside the set A. This function is defined for all A inside your sigma algebra B. In this setting, we would have that the function P is a probability function for the pair S, comma B. We now list out some properties of probability functions. Suppose P is a probability function for the pair S comma B, and let A comma B be two sets inside the sigma algebra B. In this setting, we will have that the probability of the empty set equals 0. We will also have that the probability of any event A is always going to be less than equal to 1. The probability of the complement is going to be 1 minus the probability of the event A. We will require that the probabilities will be numbers that will always lie between 0 and 1. We will have that the probability of B intersect A complement would be the probability of B minus the probability of A intersect B. And an important equation being that the probability of A union B is going to be the probability of A plus the probability of B minus the probability of the intersection of A and B. And finally, the probability of A will be always less than equal to B if we know that A is a subset of B. All of these properties follow very easily from the axioms of probability. However, let's work out a couple of examples. It's easy to notice that the set B is going to be the union of B intersect A complement and B intersect A, and this is going to be a disjoint union, which will give us that the probability of B is going to be equal to the probability of B intersect A complement plus the probability of B intersect A, which gives us the equation that we are looking for in point 5. Similarly, we can decompose A union B as A intersect B complement union A intersect B union B intersect A complement. This is a disjoint union. Applying the probability function to A union B now gives us that the probability of A union B is going to be equal to probability of A intersect B complement plus the probability of A intersect B plus the probability of B intersect A complement. And using part 5, we arrive at the equation probability of A union B equals the probability of A plus the probability of B minus the probability of A intersect B. Finally, we state two important properties. That is, if we have a partition for the sample space S, then for any B inside the sigma algebra, the probability of B is going to equal to the sum of the probabilities of AI intersect B. This is sometimes called as the law of total probability. Also, if we have a collection C1, C2, C3 up to infinity of sets inside the sigma algebra B, the probability of the infinite union is always going to be less than equal to the sum of all the probabilities of the events Ci. This inequality is sometimes called Boole's inequality. To wrap up, we have introduced some basics of set theory, introduced the notion of a sigma algebra, and we used the notion of sigma algebra to talk about probability functions associated to a sample space and a sigma algebra. We will talk more about probability functions over the course of this video series, but this is all for now. Take care of yourselves, and I will see you around.